Okay, according to the syllabus, the next kind of function we're going to be hitting are logarithm functions. And I don't know if you've seen logarithm functions or not seen logarithm functions. You might be asking, why do we need another kind of function? Well, in this little video, all we're going to do is talk about why we would need an inverse exponential function, just by looking at some examples um, and trying to make the case that the examples we could list would be in the hundreds of thousands. But here's an easy one. Says we put $10,000 into an account that is compounded monthly at an annual percentage rate of 4.2%. We can retire or quit when our account hits $1 million. When will that be? Well, in a little box, I'm just trying to summarize what we have. We know the equation for compound interest is A equals P times 1 plus R over N to the NT. Now, they told us that the rate was 4.2%, and then N was 12, so our formula becomes a little bit more easy to deal with. But here's the thing. They're not telling us the T and asking us for the amount. They're telling us the amount and they're asking for the time. That is, they're not telling us what to plug in. Another way of looking at this is that they're giving us an exponential equation, an equation with an exponential function in it, and asking us to solve for the exponent, which means that we have to find a way of getting the variable out of the exponent. Now, so far, what we've been doing is solving these graphically, but I have a number of people who are going, now, how do you do this algebraically? Well, this is what we're starting. Let's look at the second example. This is something we've seen before too. A standard 500 milligram dose of amoxicillin has a half-life of about an hour. It's like 61 minutes, but we'll leave it at this. At what time will there only be 10 milligrams left? By the way, they need to know this. This is how they determine how often you would take amoxicillin, because when it gets too low, you have to take another one. Okay, we can figure out that the equation for the amount here involves half-life. It's A equals 500 times 1/2 to the t. But here's the problem. It's the same problem as last example. We're not told the amount of time to plug in. We're told the final amount is 10. That is, we have an exponential function involved and a final answer. What we don't know is what to plug in. Another way to look at this is we need to solve this equation, which means that we have to find a way of getting the variable t out of the exponent. The third example is very similar. Like I say, there's probably 100 that we could do, but oh, well, 100,000. Anyways, in 2009, there was a pandemic involving a virus, the H1N1 virus. That should sound familiar. It was called the swine flu. The number of people who had been hospitalized with the swine flu after X days, they figured out after a while, was this fancy formula. You can see there's an exponential function involved there. P.S. 60 million people got the swine flu in the U.S. in 2009. In terms of people catching it, it was much worse than what we have right now. This formula only addresses the hospitalizations. Anyways, according to this formula, was there ever a time that 100,000 people had been hospitalized with it? And if so, when? Okay, we're going to go through the same sort of procedure we went through before. Here we're given the formula for the number of hospitalizations. That's great. But here's the problem. We're not told what X to plug in. We want to know when was the final amount equal to 100,000 and then asking for the X. That is, we have an exponential function involved. It's in the bottom of a fraction. It's easy to get out of the bottom of the fraction. It's not easy to get the X out of the exponent. Anyways, we're asked to solve this equation, which means in the end, we're going to have to find a way of getting the variable X out of the exponent. Those are three very common things. We are going to have an exponential function where someone is going to give us the answer, which means we're going to have an equation that involves an exponential equation, a function, and then we're needing to get the variable x out of the exponent. That's a common feature every time. The conclusion is, because so often when anything grows or decays, there's an exponential function involved, we will be interested in knowing when a certain answer will happen. Not plugging in the time and getting the answer. We're going to be given the answer and someone's going to say, okay, so when? Because of this, we need a function now that finds an exponent for us or gets the variable out of the exponent. This is exactly what the inverse to an exponential function would do. So right now, from the very scratch, we're going to start learning all about them.